Uh, साथियों नमस्कार. uh, Good morning to one and all. Today we are going to discuss very important theorem that is called the existence and uniqueness for initial value problem, which will involve basically the first order ordinary differential equation. So before coming to the theorem, I would like to first mention the motivation. The motivation is that uh, we can see by the three very simple examples. uh, Initial value problem may have no solution, unique solution, and infinite solution. Come to the first example. Here, whatever I have taken, mod of dy by dx plus mod of y equal to 0. Initial condition is y at 0 is equal to 1. Y is equal to 0 is clearly its solution. But if we go to the non-zero solution, we cannot get, because we can see if you divide both sides by uh, uh, mod y, so it basically become dy mod upon mod y plus mod dx is equal to 0. Once you get here the mod of log y and mod of x is equal to 0, plus is equal to some constant. After integration, if you integrate, and after integrating you get log of mod y mod of x plus some constant. If you put the initial condition, so you get value of c equal to 0. So right hand side become 0 and left side mod of two different quantity, and it will be possible only 0 when y is equal to 0. I mean log y is equal to 0, and so all are the 0. So we cannot get, and we can also see by this example, mod of two different things equal 0 definitely possible if some if both different is 0, and it is only possible when y is equal to 0. So we cannot get any y which satisfy the initial condition. So we can see clearly see that there is no solution. Similarly, let's another consider problem. Dy by dx equal to x, y0 is equal to 1. If by separation of variable, we can get dy is equal to this. Just integrate, we get the y is equal to x square by 2 plus c. And if you put boundary condition, you get c is equal to 1. So it gets the unique solution. Let's consider another problem. Dy by dx is equal to y minus 1 by x, y is equal to 1. So if separation of variable you use, then left side become dy upon y minus 1 and right side is the dx upon x. Just simply integration, and using the initial condition, we get the c is arbitrary, because left hand side is 0 in y minus 1 means 1 minus 1 0 and 0 into c, so 0 is equal to 0 into c is arbitrary. So it has infinite many number of solutions. So by the previous example, we have seen that if initial value problem is given that dy by dx equal to xy, y at next equal to y, it may have no solution, exactly one, and unique solution. So there is a natural question to find under what condition the initial value problem has at least one solution, means its system is consistent, and under what condition it has a unique solution. Here we have seen very simple problem, but if you go to the some realistic problem, it is not possible to solve very quickly. So at least we can ensure about it methods, just its solution exists or not. So to prove the existence and uniqueness, we need some very important definition, that is called the Lipschitz condition. So what is this? Suppose I have taken a function of two variable, and we say satisfy Lipschitz condition, where this xy point belongs to some region D of xy plane. If there exists a constant k, obviously positive constant, if mod of fxy2 minus fxyn less or equal to mod of ky2 minus y, means we are keeping fixed x and varying y. So first you taking y2 and y1, then we say that it is satisfy the Lipschitz condition. Now come to the very important theorems which will be used in its proof. So this is the result of real analysis, basically related to some are the of Riemann integration and some of the convergence. So first result, if we know fx is bounded and integrable on closed interval ab, then mod fx is also integrable, and mod of a to b fx dx is less or equal to a to b mod of fx dx. Means if you shift mod inside the integration, that quantity will be greater. Next important result is the Weierstrass test. What is test? Suppose a series summation fnx will converge uniformly and absolutely on AB. You might be aware about the convergence of uniformly and absolutely. Absolutely means if, since mod simply mod, and uniformly means if I say roughly, it does not depend on x. It is free from x. And if you are interested about more uniform convergence, you can see the literature, or if I receive a number of feedback, I can make separate video for the uniform convergence. So a series of summation fx will converge uniformly and absolutely on AB if what? If you able to find is convergence into summation Mn, where Mn is just is some constant, it does not depend on x, and mod of fnx is less or equal to Mn. If this series, constant series summation Mn is convergent, then we say that mod of fnx converges uniformly. This is a very, very important theorem. It is called the Weierstrass test. Next is the what about the continuity of limit function if each term is continuous. The result is that if summation fn series fnx converges uniformly to fx on AB, and its term, each term fnx is continuous, then the sum function means limit function fx is also continuous. So we will use this theorem in our proof. Next theorem is the in what condition limit may exchange from inside to outside when some integration is used. So if fnx converges uniformly to fx on AB and each fnx integrable, then the sequence a to x fnx converges uniformly to a to x fx. What is fx? Fx is basically what? This is the limit of fnx, and a to x converges uniformly means you are taking limit until infinity. Means a fnx given, if you take outside the limit and you take inside the limit, these are both are same, but when fnx is converging to fx uniformly, as well as each function fnx is integrable. So we will use these four theorems, very, very important theorems, in our coming proof. So come to the statement. So let fx be continuous in some domain of xy plane and fxy is bounded. Suppose fxy satisfy the Lipschitz condition in y as mentioned by given by equation number 2, where we have the some constant k which does not depend x, y1, y2. We define rectangle R by this mod of x minus x naught less or equal to L, mod of y minus y naught less or equal to k in D, and we restrict h and k such that m into h is less or equal to k, less than k, not equal. Then for any x minus x naught equal to less or equal to h, the differential equation, that means initial value problem, has unique solution y is equal to yx, which satisfy the initial condition also. Come to the proof. So here we use the Picard iteration concept to prove the theorem. So we know the Picard iteration formula is that ynx is equal to y0 plus integration from x0 to x fx yn minus 1 dx. If we put n is equal to 1, we get the first, n is equal to 2, we get the second. So basically what we are doing, we are, in place of finding the directly the exact solution, we basically generating the sequence of approximation y1x, y2x and y1xx, and later we will see this sequence converges to the exact solution. So basically its proof is divided in 5 parts. So first part is that if you take x between x naught minus x to x plus h, then whatever the approximation we have taken, it will always lies between the y naught minus k to y naught plus k. So by the Picot iteration, just you put n is equal to 1, so left side become y1 and right side y0 we shift, then become y1 minus y0, and we have taken mod both side, and this can be seen by the previous equation number 4. This is nothing but Picot iteration, and I am using here the mod of integration as I mentioned in the first theorem. If you go mod inside the integration, it will be the greater, and just I have done the calculation, simply integrate, you know. So here since fxy less or equal to m, so this is less or equal to m, or integration of dx is equal to basically x, and this is mod, so it become basically x minus x naught, and it is given x minus x naught is less or equal to h, and it is given m is less or equal to k as mentioned in equation number 1 and 3. So it's clearly mod of y1 minus y naught is less or equal to, say, so y lies between y naught minus k to y naught. So result is true for n equal to 1. Now I try to prove the result is true for some general n equal to yn. So this is by condition. Now I use in the Picard relation for n. So yn minus y naught, and this is the integration. I just again insert the mod inside, then it become greater or equal to, and it is again less than m by the given condition, and integration of mod dx is x minus s, so less than equal to k. So we have seen mod of yn minus y naught is also less than k, so y lies between the y naught minus k, y naught plus k for any approximation. So next we go to the second. Now we prove the some inequality which will be used in our proof. So we can say if we take means difference of successive approximation yn minus yn is less or equal to m k to the power n minus 1 upon factorial n x minus x naught to the power n. So by the previous section, if you put n is equal to 1, you will get y1 minus y naught is less or equal to m x minus x naught. We have earlier seen the first step. So what we will do? So we just here we are using the mathematical induction of second kind. So we assume it is true for some r, then we will prove that it is true for r plus 1. So we assume it is true for n minus 1, and then we'll try to prove for n. If it is true for n minus 1, you just replace n by n minus in equation 5, you will get equation 6. Now we try to prove for n is equal to n. So I try to prove yn minus 1. By the Picard iteration, you just take this difference of yn minus 1 and take the mod. You again insert the mod inside, it quantity become greater than. And here we use in the first term, this term, use the Lipschitz condition. So this become that. Now k is constant, and yn minus 1 minus yn minus 2. You have already assumed in equation number 6, it is 2. So we use this relation. And so here m k to the power n minus factorial minus constant go outside, but mod of x minus x naught power n minus is not constant. It is function of x. So you just use the x to the power n integration is power n 1 higher than divided by n plus 1. So power higher become n and then divided by n, and k is constant, and just we simplify, we will get the equation number 5. Now we come to the next step. So now we try to do whatever the sequence generating, it is uniformly converges to some function if we take x is closed interval x naught minus x to x naught plus h. So we have already seen the previous section. Mod of yn minus n is less or equal to m k to the power n minus 1 s to the power factorial for n. Now I am trying to take the summation of difference of two successive. So y naught is as it is, y1 minus y naught is less or equal to same h as given in this, Similarly, y2 minus 1, you put n is equal to 2 here. Similarly, this one. If you take m by k as common, so this will become, if you take k common, this become m into h into k. And I am taking also m common, so here basically it is k into h. Similarly, here 1 by factorial to k square h square. So this is nothing but this is exponential of kh, and 1 is missing. So to make balance, I have subtracted by minus 1. So here we will see that this sum is always finite for finite value of k, h and m. So the series m is convergent, and as we seen by the Weierstrass test, since series now series here 9 is converges uniformly. Why converges uniformly? Because I have taken mod of each term, and now since in each term here there is some h, means here x minus x naught, but finally it is converted some higher summation series, which term is now constant. So now summation mn is constant, so it is convergent. So the original series, it becomes the what? Uniformly convergent. So the series, this one is become uniformly convergent. Why? Because its each term is less or equal to some constant, and that summation of constant term is convergent. So the original series 9 is uniformly convergent. And we have seen each term of this series 9 is continuous, and so its sum function is also continuous by the theorem number, I think third or fourth by the previous slide. So what is the sum of this? So for sum we have to take, because series convergent, and we have to take infinite term series, so n tend to infinity, so it become convergence. Why? Because Ynx is nothing but, Ynx is what? If you take summation of this series y0 are equal to 1, if you expand this, each term will be cancelled. When you take n tend to infinity, right side term become the infinite series. So in nothing but this is the limit n tend to infinity Ynx, and I am saying this sum is what? Yx. So since each term is continuous and Ynx converges uniformly to Yx, so Yx must be continuous. Now we come to the fourth. Now we show that whatever the this limit point, that will basically satisfy the given differential equation. So how we, so in the previous we have proved that Ynx converges to Yx, and by Lipschitz condition y of xy minus fxyn is less or equal to k yn minus yn minus. If you take n tend to infinity, this yn become what? Y. So this becomes 0. So mod of x minus y become less or equal to 0, basically 0. So what become? Fxyn basically converges to fxy. So this also uniformly converges to y because it does not depend on x. Now, by the Picard-Station formula, take n tend to infinity to both sides. So here it becomes limit n tend to infinity, as I told, since fxynx each term is continuous and its conversion uniformly to fyx. So as by the previous theorem, limit from outside to go inside. So if you will go inside and see, this is become what? This is basically fxyx, because fxynx converges uniformly to fx. So yx become y0 plus fyx. So the right hand side, this is integrable. I mean y integrable because it is the continuous function, and this equation 11 is basically equivalent to the initial value problem. It is a very one line calculation. If you take differentiation of both sides, here become dy by dx, y naught is constant, so it differential is 0, and integration and differential is cancelled, so it becomes is basically fx of yx. And initial condition, if you put both side x by y naught, so it become y x naught. Here this is y naught, x naught to x naught. If the in the definite limit, both limit are same, value is 0, so y x naught is equal to y naught. So basically equation 11 is equivalent to the given initial value problem. So we have shown whatever the sequence of approximation generated by the uh, Picard iteration, that basically converts to the solution of that. Now we try to show the uniqueness. So this is the final step of uniqueness. So let's suppose possible capital Yx be another solution. Since small yx and capital Yx both are solutions, so it is founded, it is bounded. So their difference is some fixed quantity. Okay. Now by the Picard iteration. Since both are the solutions, so both satisfy the Picard iteration. Now I am taking here, yeah, I am inserting mod inside, so it become greater or equal. Now I am using, yeah, Lipschitz condition. So what is become k yx minus small yx and k go outside, and we have proved it is bounded, so it is k into b, like that. And here the integration of dx is nothing but x minus x naught, here some mod. Okay, so now we repeat the same. So how we repeat? We again reply here. So since here inside, here inside yx minus capital Yx minus small yx, if you again apply, you again get k into k into mod of x minus x naught and dx. So k again go outside and it is b. If you integrate, so here x minus x naught earlier, and I think, yeah, this is become square. This is typing mistake because x minus x naught is already present and dx integration is x and x minus x naught, so power become 2. So if you repeat again, so you put in place of yx minus yx naught what? X minus x naught square into b into k square upon factorial 2. So you take common. So k square and k is earlier in the original. So k cube b upon factorial 2, again this. If you again reply it, you gave the k cube b x minus n cube. So if you repeat the process n times, so basically you get the k power n b mod of x minus n factorial, where x minus x naught is nothing but this is h, this is k h to the power n upon factorial n. Now if you take n tend to infinity, this becomes 0. Why? Because kh is less than some fixed quantity है ना, capital kh is k is some finite, h is small है ना. So if you factorial n divided factorial n, and you can see by the limit idea, if denominator is factorial n, it is tending to the, because k and h is some finite quantity. Okay, so it's tending to 0. So here what we have, that difference of yx minus small yx may be, can be made small as much as possible. So we see that its mod is less or equal to 0, basically equal to 0. So inside mod that equal to 0, because mod of x is equal to 0 if and only if and only if x is equal to 0. So here we see capital Yx equal to small yx, so it has a unique solution. So thank you very much. I hope I try to explain as simple as possible. Your feedback and comment is welcome, so that next video may be improved. So thank you very much. See you later.